Welcome back. In the last video, we saw how to get visual with our data. We followed the Data Explorer's motto of visualize, visualize, visualize. And we got an idea of the training data that we're working with and the testing data that we're trying to build a model to learn the patterns in the training data, essentially this upwards trend here, to be able to predict the testing data. So I just want to give you another heads up. I took a little break after recording the last video, and so now my Colab notebook has disconnected. So I'm going to click reconnect, and my variables here may not work. So this is what might happen on your end if you take a break from using Google Colab and come back. If I try to run this function, they might have been saved. Looks like they have, but if not, you can go restart and run all. This is typically one of the most helpful troubleshooting steps of using Google Colab. If a cell, say down here, isn't working, you can always rerun the cells above, and that may help with a lower cell here, such as if this function wasn't instantiated because this cell wasn't run, and we couldn't run this cell here, which calls this function here, we just have to rerun this cell above so that we can run this one. But now let's get into building our first PyTorch model. We're going to jump straight into the code. So our first PyTorch model. Now this is very exciting. Let's do it. So we'll turn this into Markdown. Now we're going to create a linear regression model. So let's look at linear regression formula again. We're going to create a model that's essentially going to run this computation. So we need to create a model that has a parameter for A, a parameter for B. In our case, it's going to be weight and bias, and a way to do this forward computation. What I mean by that, we're going to see with code. So let's do it. We'll do it with pure PyTorch. So create a linear regression model class. Now, if you're not experienced with using Python classes, I'm going to be using them throughout the course, and I'm going to call this one linear regression model. If you haven't dealt with Python classes before, that's okay. I'm going to be explaining what we're doing as we're doing it. But if you'd like a deeper dive, I'd recommend you to Real Python classes, OOP in Python 3. That's a good rhyming. So I'm just going to link this here. Because we're going to be building classes throughout the course, I'd recommend getting familiar with OOP, which is Object-Oriented Programming, a little bit of a mouthful, hence the OOP, in Python. To do so, you can use the following resource from Real Python. But we're not going to go through that now. I'd rather just code it out and talk it out while we do it. So we've got a class here. Now, the first thing you might notice is that the class inherits from nn.module. Now you might be wondering, well, what's nn.module? Well, let's write down here. Almost everything in PyTorch inherits from nn.module. So you can imagine nn.module as the Lego building bricks of PyTorch model. And so nn.module has a lot of helpful inbuilt things that's going to help us build our PyTorch models. And of course, how could you learn more about it? Well, you could go nn.module PyTorch. Module. Here we go. Base class for all neural network modules. Wonderful. Your models should also subclass this class. So that's what we're building. We're building our own PyTorch model. And so the documentation here says that your models should also subclass this class. And another thing with PyTorch, this is what makes it might seem very confusing when you first begin, but modules can contain other modules. So what I mean by it being a Lego brick is that you can stack these modules on top of each other and make progressively more complex neural networks as you go. But we'll leave that for later on. For now, we're going to start with something nice and simple, and let's clean up our web browser. So we're going to create a constructor here, which is with the init function. It's going to take self as a parameter. If you're not sure of what's going on here, just follow along with the code for now, and I'd encourage you to read this documentation here after the video. So then we have super.init. I know when I first started learning this, I was like, why do we have to write init twice? And then what's super and all that jazz? But just for now, just take this as being some required Python syntax. And then we have self.weights. So that means we're going to create a weights parameter. We'll see why we do this in a second. And to create that parameter, we're going to use nn.parameter. And just a quick reminder that we imported nn from Torch before. And if you remember, nn is the building block layer for neural networks. And within nn, so nn stands for neural network, is module. So we've got nn.parameter. Now, we're going to start with random parameters. So torch.randn1. We're going to talk through each of these in a second. So I'm also going to put requires grad equals true. We haven't touched any of these, but that's okay. dtype equals torch.float. So let's see what nn parameter tells us. What do we have here? A kind of tensor that is to be considered a module parameter. So we've just created a module using nn module. Parameters are torch tensor subclasses. So this is a tensor in itself that have a very special property when used with modules. When they're assigned as a module attribute, they are automatically added to the list of its parameters and will appear, e.g. in module.parameters iterator. Oh, we're going to see that later on. Assigning a tensor doesn't have such effect. So we're creating a parameter here. Now, requires grad. What does that mean? Well, let's just, rather than just try to read the docstring Colab, let's look it up. nn.parameter. What does it say? Requires grad, optional, if the parameter requires gradient. What does requires gradient mean? Well, let's come back to that in a second. And then for now, I just want you to think about it. dtype equals torch.float. Now, the data type here, torch.float, is, as we've discussed before, is the default for PyTorch. Torch.float, this could also be torch.float32. So we're just going to leave it as torch.float32 because PyTorch likes to work with float32. Now, do we have this by default? We do. So we don't necessarily have to set requires grad equals true. So just keep that in mind. So now we've created a parameter for the weights. We also have to create a parameter for the bias. Let's finish creating this and then we'll write the code, then we'll talk about it. So rand n now requires grad equals true and dtype equals torch.float. There we go. And now we're going to write a forward method. So forward method to define the computation in the model. So let's go def forward, which self takes in a parameter x, which is data, which x is expected to be of type torch tensor, and it returns a torch.tensor. And then we go here. And so we say x, we don't necessarily need this comment, I'm just going to write it anyway. X is the input data. So in our case, it might be the training data. And then from here, we want it to return self.weights times x plus self.bias. Now, where have we seen this before? Well, this is the linear regression formula. Now, let's take a step back into how we created our data, and then we'll go back through and talk a little bit more about what's going on here. So if we go back up to our data, where did we create that? We created it here. So you see how we've created known parameters, weight and bias. And then we created our y variable, our target, using the linear regression formula, weight times x plus bias. And x were a range of numbers. So what we've done with our linear regression model that we've created from scratch, if we go down here, we've created a parameter, weights. This could just be weight if we wanted to. We've created a parameter here. So when we created our data, we knew what the parameters weight and bias were. The whole goal of our model is to start with random numbers. So these are going to be random parameters. And to look at the data, which in our case will be the training samples, and update those random numbers to represent the pattern here. So ideally, our model, if it's learning correctly, will take our weight, which is going to be a random value, and our bias, which is going to be a random value, and it will run it through this forward calculation, which is the same formula that we use to create our data, and it will adjust the weight and bias to represent as close as possible, if not perfect, the known parameters. So that's the premise of machine learning. Now, how does it do this? Through an algorithm called gradient descent. So I'm just going to write this down because we've talked a lot about this, but I'd like to just tie it together here. So what our model does. So start with random values, weight and bias. Look at training data and adjust the random values to better represent the, or get closer to the ideal values. So the weight and bias values we use to create the data. So that's what it's going to do. It's going to start with random values and then continually look at our training data to see if it can adjust those random values to be what would represent this straight line here. Now, how does it do so? How does it do so? Through two main algorithms. So one is gradient descent, and two is back propagation. So I'm going to leave it here for the time being, but we're going to continue talking about this. Gradient descent is why we have requires grad equals true. And so what this is going to do is when we run computations using this model here, PyTorch is going to keep track of the gradients of our weights parameter and our bias parameter. And then it's going to update them through a combination of gradient descent and backpropagation. Now, I'm going to leave this as extracurricular for you to look through, gradient descent and backpropagation. I'm going to add some resources here. There will also be plenty of resources in the PyTorch Workflow Fundamentals book chapter on how these algorithms work behind the scenes. We're going to be focused on the code, the PyTorch code, to trigger these algorithms behind the scenes. So PyTorch, lucky for us, has implemented gradient descent and backpropagation for us. So we're writing the higher level code here to trigger these two algorithms. So in the next video, we're going to step through this a little bit more and then further discuss some of the most useful and required modules of PyTorch, particularly NN and a couple of others. So let's leave it there, and I'll see you in the next video.